Chemical equilibrium evolved from the study of chemical kinetics in the following way. If we plot concentration against time for reactants, R going to products P, as we've shown you in the start of a kinetics reaction, this is 100% reactants, and over time we'll see a trend that will follow this pattern. Products will follow an opposite direction like this and level off at some point in time. So a vertical line splits these two regions into kinetic region and equilibrium region. Now, so that you will understand the differences between the equilibrium and the kinetics region, recall that kinetics region is based upon rate laws. And we write rate laws in empirical formats. That is, rate equals K, A to the X, B to the Y. For an A plus B goes to AB type reaction. If I had put a 2 in here, it would still be the same type of format for writing the empirical relationship, because the 2, which is a coefficient, does not equal the order of reaction in the kinetic region because of the change in slope. You have a constantly changing slope in here. Well, that should put order of reaction. If it does, it's only circumstantial. But the only way to determine what those X's and Y's are is through experimental observation. Run a reaction, double the concentration, see what happens. Or cut it in half, see what happens. And then you make a decision as to whether it's 0, 1, 2, 3, whatever you know about the trends. Now, when you get over to the equilibrium region and you have the same equation, A plus 2B, excuse me, goes to, let me put 2 down here, A, B, subscript 2, then the rate law order of reaction is the coefficient, because you don't have any change in slope as it proceeds as a function of time. So the rate forward reaction is K onto A raised to the first power, B raised to the second power, like that. And you can only do that in equilibrium region. Again, you can't do that in the kinetic region. Well, the one issue in this process is we call a dynamic equilibrium. When it reaches this point right here, the reaction process is entering a dynamic equilibrium. And you recall this is also called the extent the reaction as you compare this with another one. But the analysis, of course, is once you reach the extent of reaction, then that dynamic equilibrium begins to apply a different set of rules. And that dynamic equilibrium analysis is based upon what we call the law of mass action. And the law of mass action says that the rate of reaction forward is equal to the rate of reaction in reverse. That is the law of mass action, and sets the stage for developing the analysis of chemical reactions in the equilibrium region. Okay, using the law of mass action, and let's assume we have a reaction A, capital A, plus B, capital B, that's in equilibrium. The double arrows mean dynamic equilibrium. C, capital C, plus lowercase d, capital D. Now, the left-right arrow right here is a forward rate, and I'm going to put that KF. And the one right to left is K reverse, KR, like that. So what I want to do is say, okay, write the rate law expressions for the forward reaction and the rate law expression for the reverse. The reverse would be C plus D going back to A and B. So to do that for the forward reaction is rate forward equals K forward times the concentration of A raised to the A power. Remember I said you could use the coefficients in here in the rate law. B raised to the B power. Now the reverse reaction now can be written rate law, rate, reverse is KR, C raised to the C power, and D raised to the D power. So I think based on what we've learned in writing rate expressions, rate laws, empirical rate laws, in kinetic study, you should understand what we're doing here. Now, in the law of mass action, rate forward equals rate in reverse. So that means I can take the term on the right of the equal sign of rate forward and set it equal to the term to the right of the rate reverse, like this. So K forward, A to the A power, B to the B power, is now equal to K reverse, C and D, raised to the respective coefficients, little c and little d, like this. Now, the object at this point is to come up with a ratio of concentration terms, AB over CD or CD over AB, that represents an increasing number for an increasing amount of product. Solve for concentration ratio that yields increasing rate constant ratio values, or just simply increasing rate numerical values. That you'll see that's important. So what that gives us is K forward over K in reverse to equal C raised to the C power, D raised to the D power, A to the A power, and B at the B power. This term right here, Kf over Kr, is redefined. And it's called the equilibrium constant, KEQ, and it's set to that expression C and D over A and B. Like this. And if you look at it, this is products concentration over reactants. Like that. So for any given reaction, reactants in equilibrium with products, you can write an equilibrium expression that's product concentration over reactant concentrations like we derived here. And for, say, reaction 1, let's say you have reaction number 1 is reactants 1 going to products 1, and so the K equilibrium, let's hypothetically say that the products are 10 and the reactants are 1. Units and 1 unit, like that. And so, of course, that is a K equilibrium equal a value of 10. But reaction 2, let's say reactant 2 go to products 2, we're looking at, say, at equilibrium, I should be putting equilibrium, at equilibrium we find the concentration of reactants winds up at 10, okay? And the products are 1. So your KEQ for number 2, this is number 1, is 1 products over reactants, 1 over 10, which is 0.10. Now, the larger reaction, what do you see here? You have more product generated in reaction 1, and therefore the K value is significantly larger than the K value for reactant 2, which barely produced any products. So that's the purpose of the development that I'm just showing you, is that we come up with a number that represents how much product is generated or not generated, and that refers to extent of reaction. For something like reaction 1, this would have a large extent of reaction. Because it's a large number. That's what the equilibrium constant refers to. Or something like the 0.1 equilibrium constant would have a small extent of reaction, meaning from the graphic that I gave you earlier, you would have, say, reaction 1 would have a trend that looks like this to the equilibrium point. Say this extent of reaction is a 10, whereas the reaction 2, 1/10 of that. So you would have your extent of reaction at 0.1 right here. So that's what this equation is doing, telling you that this relationship in mass action is telling you what that reaction is doing in terms of its performance under the conditions specified. Now, one of the things, a KEQ value is characteristic of a given reaction. Now, when I say it is a characteristic of a reaction under the conditions specified, all reactions can be compared now. Which one will make more product and which ones will not make much product? I'll give you some examples. When studying reactions in equilibrium based on equilibrium constants, the scientific community has adopted a formatting that represents a formatting of the equilibrium constant number, whatever it is, in a way that kind of represents the reaction you're studying. For example, KEQ typically would be listed as a Kc value for gas phase reactions. All the components are gas phase. Kc value would be interpreted as a Ka value for acid reactions, acid ionization reactions, acid ionization reactions in water. And if you're studying a weak base or basic reaction, it would be listed as a Kb. This would be base reactions, base ionization, in water. Then you have the ability of salts to deliver ionization into water, and that's called a solubility product constant, Sp. Then you have some that are K values for what we call formation, called Kf, formation constants. And this is more, they all are size oriented, but this one more so than others. If you have a large Kf value, that means you get a lot of products. A small Kf, it means you didn't go very far. And there are problems when we get to certain areas in the book that are based on Kf. And also Kd, dissociation constants. And are interpreted as how much dissociation did this reaction experience. Let's see what I can. There are others. I'll leave it at that right now. So, let me zoom this a little bit. For example, acetic acid right here has this formula. Well, when it ionizes, it breaks that hydrogen off the front, and it says it's a 1.7 times 10 to the minus 5, and that says Ka value. Let me try to refocus that. And that's an acid ionization constant. Now, if you compare that, benzoic acid, here is it, and it has a monoprotic ionization. Here's its number, 6.3 times 10 to the minus 5. Well, the larger the number, the larger the ionization. Well, since this is a larger, benzoic acid has a larger K value, it's a stronger acid. is delivering more hydronium ions into solution. And you can compare any reaction, any acids in here based on that K value. So here are some examples of weak bases. Now they won't show it as an hydroxide. Like this is an ammonium hydroxide, and it has a 1.8 times 10 to the minus 5. So the ionization of ammonium hydroxide can be compared with aniline, which is shown in that second case, which is 4.2 times 10 to the minus 10. So the ammonium hydroxide would ionize far more than the aniline hydroxide form of that. So that's what these K values are about. Here are some, well, I'll just move it over here so it won't fall off the table. Lead sulfide. Look at the number here. It's 2.5 times 10 to the minus 27. Now compare that to, say, magnesium carbonate, 2 down, right here. That's a 10 to the minus 5 order of magnitude. Well, who ionizes the most in this? Well, it'd be the magnesium carbonate. Now, solubility and degree of ionization is something else. I'll show you how that connects when we get to this chapter. But the first thing you need to understand is that we're talking about compounds that have gone through reaction, in these cases ionizations, and have reached their dynamic equilibrium condition. And in that dynamic equilibrium condition, these reactions can be compared and said one does more than the other or less than the other in the course of whatever you're trying to study. The use of equilibrium constants is, again, to define extent of reaction and give an indication of how much is produced or not produced in the course of making products. When applying the equilibrium constants, one has to then learn, once you understand what it is, then learn how to apply that method or notation to a chemical equation. Consider 3H2 as a gas plus N2 as a gas in equilibrium with 2NH3 gas. The question is, what is the equilibrium expression for that reaction? Well, it's all gas phase. So we write a Kc value, and it is equal to the products over reactants. Now, the way you should couch that in your equation is it is the product of the concentration of the products, molar concentration of the product, divided by the product of the concentration of molar concentration of reactants, raised to their coefficient power. So if I were to write the equilibrium expression for this, it'd be NH3 squared coefficient divided by H2 cubed and N2 to the first power. And what those values represent is the equilibrium concentration, and they remain constant forever in a dynamic equilibrium. If you were writing one, another problem here. Here's one. CH4 is a gas plus water. This is steam, water gas, equilibrium with carbon monoxide as a gas and hydrogen gas. So again, all of them are gas phase, so you would want to use a Kc expression And these are loose in many cases, but the expression ratio is always in terms of the products over reactants. Oh, you put the state later on. It'll be important to put that state in there. And so there's your how to write your expressions, products over reactants. And we'll learn later there are variations in this, in that if these are highly different, like say the products and say one of the reactants is mega concentrations away from say the other component, whatever it is, then sometimes it's assumed that this is a constant and moved over here and redefined as something else. We'll show you that later on, but right now it's product of the molar concentration of the products divided by the product concentration, molar concentration of reactants, raised to their coefficient powers. Say you have 2HI as a gas in equilibrium with I2 as a gas and H2 as a gas, like that. Well, its concentration equilibrium constant products over reactants looks like this, of course. So there's your equilibrium in terms of molar concentrations. However, these components of this reaction being gas phase also have partial pressures. So these can be partial pressure of HI, partial pressure of I2 gas, and a partial pressure of H2 gas. And the equilibrium expression, called a KP expression, partial pressures, it's products over reactants, just like that, but in terms of the partial pressures. Like that. So those would be in millimeters or atmospheres or torrs or whatever your instrument is measuring, and would give you a KP number. Now, note, KP does not equal KC unless the sum of the molar volumes of the reactants equals sum of the molar volumes of the products. The relationship between Kp and Kc is given by this. Kp is equal to Kc, parenthesis RT, which is a gas law variable constant. T is in Kelvin, raised to the delta N power. That's the change in molar volumes, moles of reactants against the products. Now, consider 3H2 gas plus N2 gas in equilibrium with 2NH3 gas, like this. This one has 3 and 1 is 4 molar volumes, and this one has 2 molar volumes for the products. The N value in here, delta N value, is 2 minus 4 molar volumes, or a decrease of minus 2 VMs. So that minus 2 would be applied to the delta N value, and you would have to include that and RT and whatever KC, and then you could get a number that represents whatever the KP is. But what if you had this HI gas, or 2HI gas, in equilibrium with I2 gas and H2 gas, like this. Since this is 2 molar volumes and the products are 2 molar volumes, then delta N equals 2 minus 2 molar volumes, or 0 molar volumes. And so N becomes 0 in the expression here. So Kp equals Kc RT to the 0 power, which of course makes this term equal 1, and then Kp equals Kc. So sometimes you get data in a problem that's in partial pressure, but when you look at the reaction, the molar volumes are the same on both sides. So whatever value they give you for Kp is also Kc, and then you work the problem. And so it's kind of a little twist in the, what's going on in that problem. But Kp, Kc value problems are very real, and we've got them in the worksheet that we're working on. Now, before we finish today, I want to get the worksheet that I handed out to you, problems in equilibrium here, and go through a couple in here just to show you how we get started with this. So from the equilibrium problems worksheet, we want to look at reaction stoichiometry. Now what I'm going to teach you here is how to take an equation and go from before the reaction starts to the equilibrium region. So this first problem, it says 1429 in here, you're given a 2.5 mole sample of phosphorus pentachloride. Is given to be 2.500 mole, and dissociates at 160 degrees Celsius in 1 atmosphere to give, and note this, 0.338 mole of phosphorus trichloride at equilibrium. Let's see, I'm going to put at start here so you distinguish between these moles. PCl3 is equal to 0.338 mole at equilibrium, right there. Now what I want you to do is follow this pattern, and it's used many times in the near future in this course. So the reaction is given. Now give yourself a little space on the left of your page, indent over. PCl5 is a gas, is in equilibrium with PCl3 as a gas plus Cl2 as a gas. That's what they give you in the reaction. Now on the left side going down, you want to put Ci, change in C, and C at equilibrium. This is called the ICE table. ICE. Very prominent in working with equilibrium type problems. It's initial, changing, this is your kinetic region, honestly, and then this is your equilibrium region that we're working with. Well, in this kind of setup, this is like, and I mentioned this earlier in an earlier lecture, think of the reactants as being in a horse race, and the reactants are stored in a cage ready to open and let the horses run, so to speak. So before the race starts, or before the reaction starts, it says we have 2.500 mole PCl5. How much product do we have is the question. 0. So from a logical standpoint, PCl5 is still in the gate. Now mentally open that gate and let the horses run. Oh, you got to put 0 moles over here. Because it hadn't started yet. That's what I'm telling you. Now, open the gate and let them run. And it has to go through the change, the kinetic region. So this is a change relative to the coefficients. What happens? You remember how you draw the reactants? Go here, and products increase like that, right? So what you do is since the coefficient is 1, you don't know how much it drops off, you put an X there, but you have a negative X. Now, the products are increasing, so if by 1 plus X and plus X. The algebraic sum of the CI and delta C give you the equilibrium. So at equilibrium is 2.500 minus X, X, and X. 0X is X, 0 plus X, X like that. Now they gave us PCl5 at equilibrium, which is equal to 0.338 mole. So now you can extend that, knowing that one given. This one's also 0.338 mole. Now, here is 2.500 minus 0.338 mole. Like that. .162 remain at equilibrium. So that's a technique used widely in the study and working of equilibrium problems. Okay, got 5 minutes. I'm sorry. Okay. For this reaction, you're given this, and we assume 0 production in the initial stage of this. So we start out, if this is 0 over here, then the reaction moves to right to produce some of the product side. So these are going to go down, and the way you do that is enter a minus 2x because of 2 there, and this one is just simply a minus x, and on the product side it's going to go up by 2x because it's a yield, it's increasing concentration. At equilibrium, it's the algebraic sum of the initial and change. So that's 0.0524 minus 2x, 0.0262 minus x, and 0 plus 2x is, of course, 2x. Now, they go on to give us, let's see, an equilibrium mixture contains 0.0311 mole of NOBr. So this is equal to 0.0311 mole. And from this we can get X and apply it to the other two in that table and find out what the other concentrations are or what are the other mass values. So this is X equals 0.0311 over 2 mole. .016 mole at equilibrium for the NOBr, and so this one would be 0.0262 minus 016 mole. And I get 0.0102 mole at equilibrium. And this last one is 2 times 0.016 and negative plus 0.0524 0204. So that's the way you fill up this table. Now, moles are not used to calculate equilibrium constant. It's moles per liter, the molarity, and that's where we'll start tomorrow.